So far, all the probabilities that we have calculated have been theoretical probabilities. These probabilities that we would expect to happen if we could do an infinite amount of repetitions. We also have another type of probability called the empirical probability. These are relative frequencies based on an experiment or on observations of a real-life process, and you can use the E's to help you remember. Empirical probabilities come from experiments. So an example of this could be if I actually physically toss a coin 10 times and I get heads 6 out of those 10 times, then the empirical probability that I've observed for getting heads is 6 out of 10, or 3/5, or 60%. In statistics, we use probability to help us understand when something is likely to happen by chance or not. When something unlikely to happen does in fact occur, you're surprised by that and you need to investigate it further. Okay, so then it begs the question, or where we get into with this is something like, I saw 60% heads in this experiment. Is that close to what I expected to happen, or is that far away from what I expected to happen? And do I think there's any reason to investigate this coin any further? Well, probably I expect to get about 50% heads. So if I only get a little bit more than that, I got one more head than I expected, it doesn't make me surprised. I don't feel like this is a fake coin. I don't feel like I need to investigate that further. So let's look at some other ways that this might manifest. It says, which of the following events seem like they would be unlikely to occur by chance? Compare what you expect to happen, which is the theoretical probability, to what is observed, the empirical probability, in order to make your decision. Okay, so the first example says, you flip a coin 100 times and you get heads 12 times. So think about what we expect. We expect 50% of these to be heads. So let's see, 50% of 100, 0.50 times 100, we expect 50 heads. Right, that's the theoretical. What actually happened, what we observed, we got 12 heads. So what do we think? Is this close? Did we observe close to what we expected, or far away? To me personally, my feeling is that's pretty far away from the 50 that were expected. So I feel like this is far from the expected value. And I think this is unlikely to happen by chance. And it makes me have the question, is this some kind of a fake coin? Is the coin fair, or is it a trick coin? Right? So these things, whenever something unlikely to happen by just sheer chance does in fact happen, that's when we start having questions, and that's when we start want to investigate further. So I may want to do this experiment multiple more times and see if I keep consistently getting a different amount of heads far away from what I expect, and to see kind of where that leads me. Okay, the other example, my next example says, using the spinner above 100 times in a row and you land on red 15 times. So let's see, what do we expect? So in that spinner, there is one red out of 6 total. So one red out of 6 total colors. So we expect about 1/6 of the 100 spins to come out red. So that's approximately, if you divide that out or multiply that out, it's about 16 or 17, somewhere in there. Reds is what we should expect in theory. And what we observed was 15. If we expect 16 or 17 and we actually observe 15, to me, that's close to the expected value. This is very likely to happen by chance, right? I am not surprised at all by this result, and it doesn't make me have any questions about this spinner. Okay, let's see. You have a bag of 10 marbles and 4 of them are red. If you were to draw a marble at random 50 times, replacing the marble each time, how many times would you expect to draw a red marble? So again, this is expected, so this is theoretical. In theory, I'm not actually going to do it. I'm just going to say, well, how many do I expect? So let's see. 4 out of 10 of them are red. So there's a 0.4 or 40% probability of drawing a red marble. And you're going to do this 50 times. So similarly to the prior question, if we do that 50 times, we would take the 0.4 times 50, and that brings us to 20 times that we think that it should come out as a red marble. Okay, what these are sort of leading us to, these examples are leading us to, is what's called the law of large numbers. It says if your simulation is designed correctly, then the more times or the more trials that you do, the closer you should expect your empirical probability to come to that true theoretical probability. As you approach infinitely many trials, the empirical probability and the theoretical probability approach the same value. Okay, so this is why it's not enough to simply do one trial and call it a day and say, well, this was my result, so this is what it is. This is why you have to repeat your experiments over and over and over again. The more trials you do, the more likely you are to have accurate results that match up with that theoretical probability. So the following graph shows a plot of empirical probabilities, and it shows how they can change a lot with each addition of a new coin flip. So this is specifically coin flips. So this is tossing a coin and recording when it comes up heads. So at first, this is wildly different, but as you increase those trials, notice that empirical probability sort of settles down, they say, to what we know the theoretical probability is of 50%. So here at the beginning, it changes very wildly, and then it sort of settles down to that 50% mark way out here. So notes on that are, if your simulation doesn't eventually settle down to the theoretical value that you expect, then there are basically two explanations. Either your theoretical value is incorrect. So what you've thought all along for your whole life, or what you've been told about flipping a coin should be 50% heads and tails, if you cannot ever get your simulation to settle down to that, maybe it's wrong. Maybe that's not really what it is. Okay, so we're going to get into that later on in the semester of testing what we are told to be true, and do we have enough evidence to say that's not really true? Or your empirical value is just varying because that's what empirical probabilities do, and you need to do more trials. So maybe you've done 1,000 trials and you feel like that should be enough, but maybe it's just not. Maybe you need to do 2,000, 3,000, 5,000, 10,000 trials in order to get that empirical probability to settle down. Another note is on streaks. So to understand that no single outcome is ever, quote, due, if you flip heads 8 times in a row, tails is still no more or less likely to occur on the 9th flip if you have a truly fair coin. So don't get caught into trick games like casino games and things like that, where you see that it appears that a streak is happening, so you bet on the other value. That's not a good way to do things. Nothing's ever due to happen. And then it says, look closely at this graph. Can you tell what the first flip landed on? And can you see why you cannot stop after a single trial in an experiment? So if you look closely here, the very first dot that was recorded was up here at 1. That means after the first trial, it is showing a 100% chance of landing on heads. So that first flip must have landed on heads. But do you see why you cannot stop there? I cannot flip a coin one time, observe a heads, and then go tell the world, hey everyone, you have a 100% probability of flipping heads on all coins. Right? You can't stop there. So as it moved on, the next flip, notice the dot went down. So in the next few flips, okay, I must have flipped some tails because my probability is dropping now. And then it dropped and dropped, and eventually again kind of bumbled. It kind of went up and down until it settled at around the 50% mark.